audience, for what values does this series converge? Studio audience, what do you think? Anything less than 1. So R less than 1, like that. Okay. Anything else you want to add to that? So then this would converge for like R equals -2. That's less than 1. It'd be greater than 0. Okay. All right. What kind of series is this? It's a geometric series. Yeah. And way back in the beginning of this section on series, we looked at geometric series and we determined 2 things. We determined what values for R it converges, and we also determined what it converged to, right? Because most of the time we can say it converges or diverges, but we don't know what. Geometric is one of those rare examples. So what we determined a while back, as long as R was a proper fraction, didn't matter whether it was positive or negative, this converged. Because if you repeatedly multiply by a proper fraction, you're going to keep shrinking and shrinking and shrinking to 0. So yeah, so it could be all the way up, but anything between -1 and 1 will work. So R equal 2 does not work. Do you guys remember the value this converges to? It's a fraction. It's got a 1 in the numerator, a 1 in the denominator. There's also an R in the denominator, and they're connected by something. Subtraction. Good job. Yes. So this will converge to 1 over 1 minus R. And we had a cute little trick to make that happen, kind of related to like 1/3 equals 0.33333. I started off with that example, which is a geometric series. So this is the value it actually converges to if, right, often we'll say the absolute value of R is less than 1, which is the same thing as saying that right there. Okay. Now, if R is 1, I have a problem. There's a 0 in the denominator there, okay? And 1 over 0, physicists say 1 over 0 is infinity. Depends on how you approach it in math. But if we try to add 1 plus 1 plus 1 forever, yeah, that grows forever. If R is -1, we didn't explore that one yet, I don't think. Or maybe we did. Let's see what happens if R is -1. We'll get a 1 minus 1 plus 1 minus 1 plus 1, and it just continues like that forever. If we look at partial sums, the 0th sum is 1. The first S sub 1 would be 1 minus 1 or 0. S sub 2 would be a 1. S sub 3 is 0. So the sequence alternates. +1, -1, the sum, the partial sums alternate between 1 and 0. Do they converge then? What do you think? What does it mean to converge? So convergence, what it means is that the limit as n gets big of the partial sums, which I have listed coming down there, oops, arrow that way, has to equal some real number. One real number. Yeah. Anything else is not convergence, which is divergence. So here we have to say this diverges because it doesn't converge to a single real number L. This diverges. And we talked about earlier, there are many ways to diverge. Something can grow without bound, it can drop without bound, or something can oscillate, which is what this is doing. And here we're oscillating between 2 numbers, something can oscillate between 4 numbers, or 10 numbers, or 20 numbers, so all kinds of stuff can happen. But convergence means that we're heading toward a particular number and we can get as close as we ever want to it. We can always control the error. That's the key, controlling the error. All right, so R is a cool letter. It makes a lot of sense in geometric series because it's a ratio of consecutive terms. Okay, what that means is, for example, there's an nth term somewhere, and right before that is the n-1th term. And if I take the ratio of those consecutive terms, what do I get? Well, that would be r to the n minus 1, which would be r to the first or just r, right? So that's one reason they use r. What's our favorite letter to abuse in mathematics? X, yeah, so I'm just gonna rewrite this in X just for fun. So I could, instead of an R, I could just say, let's look at the series 1 plus X squared. Now, if I just write the first few terms, like this would be S sub 2, sorry, the second partial sum, that's a polynomial, right? S sub 3, 1 plus X squared plus X cubed, that's just another polynomial. Now, generally, we're not just interested in the partial sums, we're interested in watching what happens as we let the sum grow forever. So S, no subscript, is that infinite series as k goes from 0 to infinity of x to the k, which would be 1 plus x squared, dot, dot, dot. Eventually, there's going to be something called whatever k is, and it just keeps going forever and ever and ever. Once I go forever, it's no longer a polynomial. Polynomials are finite things in terms of the number of terms they can have, right? Because we classify polynomial by degree. This is a polynomial of second degree. This is a polynomial of third degree. Big question, can we have a polynomial of infinite degree? And it turns out we can, and they're called power series. So a power series is a polynomial of infinite degree. Which is kind of crazy because infinity is a problem. Sometimes, however, that infinitely long polynomial converges to something. That's a 3, believe it or not. In this case, we know from our work with geometric series that it converges to 1 over 1 minus x, where the first term is this guy in the numerator, and my base is that guy right there. All I'm doing is renaming it as x instead of r. Okay, would you agree that 1 over 1 minus x is a function? Okay, that means a power series can be a function too. Polynomials are nice. You study a lot of them in algebra and pre-calculus. Their domains are all real numbers. However, once we cross that line from going from finite to infinity, weird stuff happens. So what's the domain of this bottom function? Not this one right here, this one right here. Well, earlier you told me this only converges if the base is between -1 and 1. So that's its domain, okay? So the domain of this one is that set of x values right there. You pick one of those x values, we'll get an answer out of it. If you pick some other x value, we're not going to get an answer out of it, okay? This is called the interval of convergence. So because we're talking about series and infinity, we have to talk about convergence. So another name for the domain of a power series is its interval of convergence. If I graph that interval on a number line, then I might do something like put an open circle at -1 and an open circle there and then shade everything in between. Sometimes instead of open circles and closed circles, people like to use parentheses and square brackets. You guys have seen that too, right? Okay. So an interval of convergence, any interval has a width, and every interval has a center. So in this particular example, the center is x equals 0. And with power series, instead of talking about the width of the interval, we talk about the radius of the interval. And the radius would be the distance from the center to either edge. So here, the radius of convergence is 1. So now I'm using R in a different way than I was before. Before I was using R as the base for a geometric series. Here I'm using R as the distance from the center of my interval to the edge of the interval. At first, a lot of the series we look at will be centered at 0, but they don't have to be centered at 0. They could be centered somewhere else, at 1 or 2 or -5, at pi. You can center them anywhere you want. But just for simplicity, we'll center them at 0. If it's not centered at 0, so if we try to center it at x equals, let's say, a, then the series will look a little different. Instead of powers of x, you'll have powers of x minus a. Oops, I don't want to use an a there. Get rid of that. So a power series that's centered at a would look something like this. You have some kind of coefficient out front. That coefficient may be dependent on n. And then instead of a power of x, you have a power of x minus a. So if this converges, then what'll happen is we'll get something like, remember before we had the absolute value of x was less than 1? In this case, we'll get something like the absolute value of x minus a is less than something. Could be 1, maybe not. So usually we put a capital R there at the end. So a is some fixed number. So for example, I could have the sum as n goes from 0 to infinity of just x minus 3 to the power n. Here I'm letting my b sub n's be 1 all the time, right? That's like the simplest I can make it. But the b, we'll look at some more complicated b sub n's in a minute. So my claim is 3 is the center of my interval. X is a variable. X could be any number. For some x values, this thing will converge. For other x values, it will diverge. And we'll explore that in just a minute. When I look at this right here, what this tells me is that absolute value means distance from 0 usually. When you do a minus something inside, that means I want to know how far is x from a. Okay, so the geometric interpretation of this inequality is the distance from x to a must be less than r. So if I look at that on a number line, a is the center of attention here. X is some number to the left or right of a, I don't know which. But what I want to make sure is that if I move r that way, that would put me at a plus r. Or if I move r that way, that would put me over here at a minus r. X has to be some number in that interval here. That's the interpretation of that guy right there. Does that look familiar? You remember seeing that before? Clint, you got an ugly face there. You got an ugly face there, like you don't like that. Okay, does my interpretation make sense here?
Yeah, I understand what you're talking about.
Yeah. Okay, yeah, so sometimes you'll see that in algebra classes before, sometimes you haven't. Have you seen it before? Doesn't look familiar either? Okay, so just another way I could break this down, I could just do it algebraically instead of geometrically. So algebraically, Absolute value is a piecewise function, right? So if I want to break down something like the absolute value of x minus a is less than r, then there's two different cases. Either x minus a is less than r, provided x minus a is positive, right? If the inside is positive, you don't have to do anything. So if x minus a, let's see, positive would be greater than 0, right? And I can actually get away with greater than or equal to 0. So as long as x minus a is greater than or equal to 0, then this is real straightforward. However, what if x minus a is negative? What happens? Like, what's the absolute value of negative 2? 2. We take the opposite of whatever is inside. So if x minus a happened to be negative, then I have to take the opposite of x minus a, and that should be less than r. If I clean this up a little bit, the top inequality, let's bring that over here, says adding a to the other side that x has to be less than a plus r, which is what I was claiming in this right side of my picture here. And then if you explore the other side, well, I have two options. I could either multiply that negative through, or I could multiply it to the other side. I'm going to multiply it to the other side. If I do that, then I'm going to get x minus a is greater than negative r. Adding a to the other side, I get x has to be greater than a minus r. And I have to meet both of these conditions. So this one has to be true and that one has to be true. So back to this picture here, and let's pick a different color right there. So the first one says the x value has to be less than, oops, I wanted a highlighter. This one says I have to be less than a plus r. The other one says I have to be greater than a minus r. If they're both true, that means we have to meet in the middle there. Okay, so there's the algebraic version of it, the geometric interpretation of it, but we're going to see this a lot. Pretty much every problem we do is going to involve some interval, sometimes centered at 0, sometimes it's centered somewhere else. Sometimes r is 1, sometimes r isn't. Okay, so let's play around some more. Let's look at a relatively simple one. Let's suppose that I have the series, pen please. I wrote down a cute example. Oh yeah. 1 plus 2x plus 3x squared plus 4x cubed. Keep going. Often we like to write in summation notation, but it's not absolutely necessary. I'm going to do it here. So this is the sum as k. It makes sense to start with 1, given the 1 up there, maybe. Okay, or you could start with 0. It's up to you. What do you want to start with, 0 or 1? Sorry, I just biased you with that. You like 0 better. That's a good idea. Okay, let's start with 0. All right, so if this is k equals 0, that's k equals 1, 2, 3. Then let's see. What do I have? Well, it looks like my multiple is k plus 1, and my power is k. So if I plug in 0, I get 1 times x to the 0, which is 1. If I plug in 1, I'll get 2 times x to the first. Okay. So this is what my series looks like there. Now I want to figure out, when does this converge and when does this diverge? Would you agree this isn't a straight geometric series? Straight geometric series, I wouldn't have the 2 times 3 times 4 going on there. So it's not straight, but it's kind of like a geometric series. So my favorite tool for determining if something converges or diverges, anybody remember? The ratio test. Yeah, so I'm going to apply the ratio test here. Ratio test. So ratio test says, okay, what you want to do is you want to look at the absolute value of a sub k plus 1 divided by a sub k. And we learned the trick the other day in class that it's better to think about that as a sub k plus 1 times the reciprocal of a sub k. So let's see. If I replace k with a k plus 1 there and there, then I'm going to get the absolute value of k plus 2 times x to the... Actually, no, I can write this as the ratio. That'll work out fine. This one doesn't have a denominator. At least the terms don't have a denominator. All right, so we're going to write it as a fraction. So k plus 2 times x to the k plus 1 divided by k plus 1 times x to the k. And then we're supposed to clean that up as much as possible and then take the limit. So does anything clean up here? Well, the k plus 1 over k plus 2, I'm kind of stuck with those since k is a counting number or a whole number. It's never negative. So I can kind of pull that out of the inequality. Sorry, out of the absolute value. So I have a k plus 1 over k plus 2. No, reverse that. And then what happens with x to the k plus 1 divided by x to the k? That's just x to the 1, and it's in the absolute value. So I am stuck with the absolute value of x because I haven't determined that x has to be positive. It could be anything. All right, and then I'm supposed to take the limit of this for the ratio test. So what is the limit as n gets huge of k plus 2 over k plus 1 times the absolute value of x? Well, absolute value of x is just chilling out. It has nothing to do with k. There's no k's there. What's the limit of this ratio? It's 1. So this is equal to just the absolute value of x. Oh gosh, k's and n's. K, thank you. Yeah, that helps. All right, what does the ratio test say about when this limit should converge? If it's less than 1, yeah, the ratio test says if the limit is less than 1, then this will converge. So if I pick any number absolute value-wise less than 1, this should converge. So if I said, hey, x equals 1/3, this should converge. If I said x equals negative 1/3, this should converge. Okay. So let's check that out. Let's plug one of these in and see what happens. So what if I try? Let's see. If I take, let's pick a new color. What are we doing? Good. Sum as k goes from, let's see, I think we started with 0 to infinity of k plus 1. And we're letting x equal negative 1/3. So I would have negative 1/3 in parentheses to the k. All right, what's that going to look like? Plug in some numbers. If k is 0, I get 1. If k is 1, well, let's see, this guy here will be a negative 1/3. So it's going to be a minus 2 times 1/3. And then I'll have a plus, and that one will be what, 3 times 1/9. And then I'll have a minus again. 1, 2, 3, 4 times 1/27. This is k equals 0, 1, 2, and 3. Yeah, and then that just kind of keeps going. Do we believe that's going to converge? Let's see, that would be what, a 1 minus a 2/3 plus a 1/3 minus a 4/27. What would be next? Plus 5 over 81. And it's just going to keep going like that. The terms do appear to be shrinking, right? Yeah, going to 0. Just because they go to 0, does that mean it has to converge? No. Divergence test says if it doesn't go to 0, it diverges, but we don't know the other way. But what do I know also here? It is strictly alternating. So it's strictly alternating the the terms, non-negative, are going to 0, so this thing has to converge, which is what the ratio told us anyway. Okay, the ratio test already told us that. What the ratio test doesn't tell us is what's happening on the fringes, on the edges, right? So what we know right now is we have convergence in between 1 and -1. The ratio test is inconclusive at 1. That means we need to find another test at 1. So let's just check to see what's happening at 1. So new, if x equals 1, then I'm going to get the sum as k goes from 0 to infinity, k plus 1 times 1 to the k. Well, 1 to the k is pretty boring, right? So this is just 1 plus 2 plus 3 plus 4. That's a problem. Divergent on that endpoint. Then we check the other endpoint. If x equals -1, sum k goes from 0 to infinity, k plus 1 times -1 to the k. Kind of sort of similar, except it alternates. 1 minus 2 plus 3 minus 4 plus 5, and so on. It strictly alternates, but are the 1, 2, 3, 4 going to 0? No, so it's divergent. Just to double check, if you looked at partial sums, the first partial sum is 1, the next partial sum is -1. So 1 minus 2 is -1 plus 3. Oops, sorry, I got ahead of myself there. Interesting. -1 is the second partial sum. The third partial sum would be 2. And the fourth partial sum would be -2. Fifth partial sum would be 3. Guess what the sixth one's going to be? -3. Yeah, it's going to oscillate and it's going to grow. Okay, so it's definitely divergent by the alternating series test and by observation. Observation isn't good enough for a proof, but it's good like to double check with some numerical things there. Okay, let's try another one.
It looks like it's divergent.
It looks like it's divergent to me. Yeah, I like that. You can always try that. I mean, you might get some points. Yeah. All right. How about do one more example, then I'll set you free early. Ooh. Ooh. All right, let's go hardcore. All right, so we're going to try the sum as n goes from 1 to infinity of -1 to the n times x to the n divided by 3 to the n times n squared plus 5. Oh, that's not the one I wanted. Oh well. We'll go with it anyway. I wanted the next one on my list. Okay, so it's usually not a bad idea to list out a few terms, in which case a program like GeoGebra or Desmos is nice. So I'm going to skip that one for now. I'm going to jump straight to the ratio test. Okay, so since this one is a fraction, I'm going to do multiply by the reciprocal trick. So I need to consider the absolute value of -1 to the n plus 1 times x to the n plus 1 over 3 to the n plus 1 times parentheses n plus 1 squared plus 5. Times the reciprocal of the original thing up there, which would be 3 to the n times n squared plus 5 over -1 to the n times x to the n. And then we pray stuff disappears, and usually with the ratio test, lots of stuff goes away. Well, I'm inside the absolute value, so I can safely say you guys aren't needed anymore. They don't cancel. That's a lie. I drew it that way, my apologies. But because of the absolute value, I can ignore them. X to the n goes into x to the n plus 1 x times. 3 to the n goes into 3 to the n plus 1 3 times. And then I'm left over with that polynomial stuff. So I'm going to rewrite at this point. So what do we have? We can't get rid of the absolute value yet because we still have x hanging around in there. So I'm going to leave the absolute value for now. In the numerator, I have an x times n squared plus 5. In the denominator, I have 3 times parentheses n plus 1 squared plus 5. Extra parentheses to be careful that I catch everything there. Yeah, okay. And there's really not much I can do to simplify this, so I'm ready to take the limit as n grows. All right, so as far as this limit goes, the x and the 3 have nothing to do with this, so I'm going to have an absolute value of x over 3 for sure. In the numerator, I have a quadratic polynomial. In the denominator, I have a quadratic polynomial. They're the same degree. Their leading coefficients are 1 and 1. So this part right here, as n gets big, must go to 1. So all that's left is the absolute value of x over 3. What does the ratio test say about that limit? Ratio test says that limit has to be less than 1. Usually with an interval like this, I want to solve for x. 3 is a positive number, so I can multiply both sides by 3. So new page, I get absolute value of x has to be less than 3. Oh, this is a wider interval than we saw before. And I mentioned that before. Sometimes the interval can have a radius of 1, sometimes it's less than 1, sometimes it's greater than 1. So here the radius is 3. So drawing this, because I'm looking at powers of x, it's centered at 0. Which kind of makes sense here. This says x is some number that's between 3 and negative 3. So 0 is my center. If I go 3 to the right or 3 to the left, I have to stay within those boundaries. What the ratio test doesn't tell me is what's happening at those boundaries. So then I need to whip out another test. So x equals 3. If we plug it back into that craziness right there, let's see. Ooh, this is kind of nice. That'll be 3 to the n over 3 to the n. Okay, so then I'll just get negative 1 to the n over n squared plus 5. So then I'll have the sum as n goes from, I think it was 1 to infinity, of negative 1 to the n over n squared plus 5. Okay, what are some observations about this guy here? It's strictly alternating. And if I ignore the alternating part, the limit as n gets big of 1 over n squared plus 5, that sucker's 0. So this thing must converge. So this time I got to extend my interval. In the last couple examples, the endpoints didn't converge. This time, the right endpoint converges. Let's plug in the left endpoint and see what happens. I'm going to write a little more detail for the left one. On the left side, I'm saying x is negative 3. So then I'll get the sum as n goes from 1 to infinity of negative 1 to the n. I'm replacing x with a negative 3. In the denominator, I have a 3 to the n times n squared plus 5. What can I say about that pair? They have the same power, right? So that means you can rewrite them as a single fraction. So I can say that that must be the same as -3/3 to the n. -3/3 on a good day is -1. So what I have up there is then a -1 to the n times -1 to the n. And they do have the same power, right? So that means this is the same thing as -1 times -1 to the n, which is just 1 to the n. So the alternating part goes away in this case. Okay, they balance each other out because they're alternating at exactly the same frequency. So now I have the sum.
You could do it the other way and say, just like at the numerator and add those together.
Yeah, you could have done that too.
Just cancel them.
Yeah, yeah, there's lots of order operations. Yeah, so you could have just brought those two together, say, hey, that's just 3 to the n, divided by 3 to the n is a 1 all the time. Yep. So now we just have 1 over n squared plus 5. Okay, what does experience tell us about that one right there? It kind of, if the 5 wasn't there, it'd be a convergent p-series, right? Let's see. We just made the denominator bigger by adding 5. So this guy right here is less than the sum as n goes from 1 to infinity of 1 over n squared, which is a convergent p-series. P equals 2, which is less than 1. Greater than 1. Sorry, wrong direction. Greater than 1. And so it's convergent. So by direct comparison, this is convergent. So this is convergent. Convergent by direct comparison. So backing up a step, we now know that it's also convergent on the left side. And so the homework problems are basically going to be, here's a power series, usually the ratio test to find the radius of convergence. And the ratio test really only finds us the ratio of convergence, which is part of the interval. Then we have to separately go test each endpoint to figure out the interval. And sometimes it diverges at both endpoints. Sometimes it converges at both endpoints. Other times it'll converge at one and diverge at the other. You never know till you check each endpoint. So the procedure for power series is pretty much the same at first. First step is usually to apply the ratio test. To get the radius of convergence. Okay, so that gives us a start at our interval. Second step is to test the endpoints of that interval. And the interval is always based on the center and the radius. And at first, all of our problems have a center of 0, but don't let that deceive you. Always double check. Is my center really 0? Because sometimes it's not going to be. So the homework I have broken up, the first, I think, 9 problems have a center of 0, and then the rest have some other center. And we'll do more with those tomorrow. 3, just state your interval. Seems kind of simple. There is a lot of work in there because simplifying the ratio test is a lot of work. Then you got to find a different test for each endpoint. Often the alternating series test will work on one side or the other, sometimes even both. Just kind of depends on the series. All right, I'm going to shut up now. You guys have a good day and do good math.